In the previous part, we learned how spin currents can manipulate magnetization and the different excited states that can be generated. Now, I'd like to consider how such spin currents can be used to control the magnetic domain walls and other interesting textures. We will start by the ideal one-dimensional domain wall, and we'll see that the physics involved is actually quite rich, with different torques leading to different behaviors. We'll also talk about chiral domain wall motion, which is a very hot topic at the moment because this wall can reach very, very high velocities. Then we will talk about the emergent electrodynamics, where the magnetic textures in 2 or 3 dimensions can generate funny effects like topological Hall effect or topological torque. Finally, we will conclude by talking about magnetic vortices and Skyrmion dynamics. So if you're hungry, let's go for it.
I explained in the first lecture that the idea of driving a magnetic domain wall with a current was first proposed by Luc Berger in 1978, and that he even estimated the current density that would be needed to move the wall. It took about 30 years to observe the current-driven domain wall motion because at that time the technology was not mature enough. With the development of microfabrication and magnetic imaging, current-driven domain wall motion was finally reported in 2004 by several groups worldwide. Here I show the images recorded by Yamaguchi and co-workers at Osaka University. You see that the domain wall moves along the electron flow and changes direction when changing the current polarity. Very quickly after that, Stuart Parking from IBM proposed to use this effect in a device called the racetrack memory. This device is a shift resistor, where the information is represented by the presence or the absence of a domain wall, and the wall itself is moved by a current. In this lecture, I'm going to explore the physics of the interaction between spin currents and domain walls. But if you want to learn more about the state-of-the-art of this field, you can look at these very nice reviews. Before we get into the physics of spin transfer torque, let's remind ourselves how field-driven domain wall motion works. I have a block wall and I apply a magnetic field along one of the magnetic domains. This field exerts a torque on the magnetic moments, and if I look at the moments at the center of the wall, it tends to take it along the wall direction, which means that it favors the nail configuration. In addition, the magnetic damping tends to bring the magnetic moment upward. Once the magnetic moment has been brought away from the block configuration, there's a reaction from the dipolar field that does 2 things. First, it induces a precession around the demagnetizing field, so along the damping field, and it also creates a demagnetizing damping that counteracts the field torque. So 2 things happen, as long as the field torque compensates exactly the demagnetizing damping. The domain wall is stabilized in a configuration that is in between the block and the nail configurations, and then we have a steady motion. And when the applied field exceeds the demagnetizing damping, the central magnetic moments start precessing continuously, and we enter in the regime of precessional motion. For more information about the physics of field-driven domain wall motion, have a look at Lecture 5. Now, I want to consider the motion induced by spin transfer torque. What happens when I inject a charge current along the wall? I will assume that during the motion, the domain wall remains rigid. To get the wall profile, we consider the following magnetic energy density with exchange, uniaxial anisotropy, and dipolar anisotropy. I inject the magnetization vector in spherical coordinates and I obtain this expression for the polar angle. Here I have the chirality of the wall, its velocity, and the domain wall width that I consider as a constant. The azimuthal angle that tells you whether the wall is block or nail is also a time-dependent variable. Okay, now let's look at the torque. How does it look like? Remember that for a spin valve, it has this M cross P cross M configuration. You can think of a domain wall as a series of spin valves in which the magnetization of the polarizer and that of the free layer form a small angle. In other words, I can express the polarization P as a small deviation from the magnetization M. As a result, the torque looks like that, with a coefficient Bj that has the dimension of a velocity and is proportional to the spin current polarization P and to the current density Jc, and is also inversely proportional to the saturation magnetization Ms. This torque is called the adiabatic torque. You can notice that if you replace the spatial gradient, dm over dx, by the inverse of the domain wall width, you get the effective field predicted by Berger in 1978. Beautiful, isn't it? Now that we know the form of the torque, what does it do? I insert the torque in the LLG equation and I analyze the impact of the three torque terms on the domain wall dynamics. The spin torque term brings the magnetic moment either upward or downward, depending on the sign of the current. There's another torque that comes from the combination of the spin torque with the magnetic damping. And if I replace this dm over dt by this one, I obtain a contribution that is proportional to both the damping and the adiabatic torque parameter. This torque counts the central moment away from its rest position and changes the domain wall from block to nail configuration. When I add the torques coming from the dipolar field, I see that the adiabatic torque competes with the dipolar field, and that the adiabatic damping competes with the dipolar damping. Let me now inject the rigid form of the domain wall into the LLG equation to get the equation of motion of the wall. I obtain this set of coupled equations for the velocity and the azimuthal angle. For these equations, I get two regimes. When the adiabatic torque is smaller than the critical field, which is nothing but the Walker field, in fact the central magnetization counts away from its rest position and simply stops when the torque and the dipolar field are equal to each other. So there is no motion below Walker breakdown. Once the adiabatic torque exceeds Walker breakdown, then I enter the regime of precessional motion. This is very similar to the field-driven motion. In other words, the only way the adiabatic torque can induce domain walls to move is when it exceeds Walker breakdown. This is a conclusion reached by Zhang and Li in their landmark paper in 2004. This is very important because it means that the adiabatic torque cannot induce steady motion, but only precessional motion, which is much slower. The problem with the adiabatic torque is that it could not explain the experimental data when domain wall motion was observed at much smaller current densities than expected. So one had to come with another explanation, or another torque. And this is what Shufeng Zhang and André Thiaville proposed independently in 2004 and 2005. As I already mentioned in the previous lecture, anytime we have a certain torque T, spin diffusion effects induce a correction of the form m cross T. So, why not introducing a phenomenological torque of the form m cross dm over dx? This torque should be proportional to the current density, and therefore it is usually parameterized by the parameter beta, which is wrongly called the non-adiabatic torque. I say wrongly because this torque does not necessarily come from the non-adiabatic spin dynamics, but that's for the next slide. Let's get back to our one-dimensional model and see how this new torque modifies the dynamics. The non-adiabatic torque enters here. I now reorganize these two equations to obtain an explicit expression of the velocity and of the equation of motion of the azimuthal angle. I proceed to the same analysis as in the previous slide, but accounting for the non-adiabatic torque, and I get this picture. You see that now the non-adiabatic torque competes with the adiabatic damping. As a consequence, I obtain two distinct regimes. When the adiabatic torque is below Walker breakdown, the azimuthal angle is stabilized between block and nail configurations, and I still get a steady velocity that is proportional to the ratio between the non-adiabatic parameter beta and the damping alpha. Above the Walker breakdown, I obtained the same scenario as before with the precessional regime. The current velocity characteristic we expect is given here in these nice calculations performed by André Thiaville, where we clearly observe these two regimes. Importantly, you see that if the ratio between beta and alpha exceeds 1, then the velocity is much faster below Walker breakdown. We have seen what the non-adiabatic torque is capable of, but we haven't talked about its physical origin. In the next couple of slides, I'm going to present two main mechanisms that have been proposed. The first one is called spin mistracking and was proposed by Gen Tatara in 2004. And yes, 2004 is the glorious year of current-driven domain wall motion. The idea is to consider how the electron wave function propagates in a magnetic domain. Because of the SD exchange, the domain wall acts like a magnetic impurity, so that an incoming wave is not only transmitted but also reflected. The amount of reflection is directly related to the ability of the electron spin to follow or to keep track with the magnetization of the wall. So one can see that in a smooth and large domain wall, the electron spin remains mostly aligned on the magnetization direction, and therefore the reflection should be small. On the contrary, in a narrow domain wall where the magnetization changes direction quickly, the electron spin has a hard time to keep track, and a small mistracking appears, leading to enhanced reflection. What Tatara demonstrated is that in this regime, the domain wall velocity is directly proportional to the domain wall resistance that comes from the spin mistracking. The narrower the wall, the larger the mistracking. The larger the resistance, the larger the velocity. Interestingly, one can demonstrate that the domain wall resistance, and therefore the velocity, is related to the domain wall width through an exponential decay, pretty much like in quantum tunneling. The scale is given by the spin dephasing length, that is to say the length over which the spin aligns along the magnetization. So the effect is significant only for domain walls whose width is of the order of the spin dephasing length. This scenario has been studied and confirmed numerically. However, the simulations show that the torque induced by spin mistracking is in general very small and can be substantially enhanced by putting disorder in the system. This calls for an alternative scenario. The second scenario was proposed by Shufeng Zhang the same year and has to do with spin relaxation. Let's get back to the familiar spin-drift diffusion equation, where we have the divergence of the spin current, the spin precession around the local magnetization, the spin dephasing, and the spin relaxation. I'll spare you with the math, but I can derive an expression of the spin torque, assuming that the divergence of the spin current is non-zero. I get two perpendicular components. The first one is mostly the divergence of the spin current, whereas the second one is proportional to a parameter that accounts for the interplay between spin relaxation, dephasing, and precession. In the adiabatic limit, the spin current is simply proportional to the current density times the polarization, and it is spin polarized along the local magnetization direction. For consistency, I need to average the spin current over a magnetic unit cell, so I get this expression. When I inject it in the expression of the torque, I finally obtain the familiar formula with the adiabatic and non-adiabatic torques, where I recognize the coefficient Bj, which is also called the spin drift velocity, and the non-adiabatic parameter beta that is governed by the ratio between spin precession and spin relaxation times. If I want to be complete, I should in fact take spin diffusion into account, and the spin current should look like that, where the second term accounts for the fact that electrons diffuse across the wall, introducing non-locality. The revised expression for this torque is here, where the third term is proportional to the square of the spin dephasing length. This means that narrow domain walls will experience enhanced non-adiabatic torque even if the spin mistracking is too small. In fact, the non-adiabatic torque decreases quadratically with the domain wall width. We have looked at what the theory says, Now let's look at the experiments. It took a long time for the technology to be mature enough to enable the observation of current-driven domain wall motion. In 2004 and 2005, several groups around the world managed to observe this motion using various optical and electrical detection techniques. I have already mentioned the work from Yamaguchi and co-workers. Here I'm showing the images taken by Matthias Klaue by spin-polarized scanning electron microscopy. Here, the experiment is performed on a permalloy wire that is wide enough to enable the formation of nail walls as well as vortex walls. And when a current is injected in the wire, the wall can pass from one configuration to the other. When we look at all these pioneering experiments, what is very clear is that the adiabatic torque is not sufficient to explain the observed threshold. As I mentioned before, the adiabatic torque can only drive domain walls if the current exceeds the Walker breakdown, which typically corresponds to 10 power 13 ampere per meter squared. And the threshold reported in the experiment is rather 1 to 2 orders of magnitude smaller than that. So it means that the motion is rather due to the non-adiabatic torque, and that the non-zero threshold is associated with extrinsic pinning centers that prevents the domain walls from moving at arbitrary low current density, and that the non-zero threshold is associated with extrinsic pinning centers that prevent the domain walls from moving at arbitrary low current density. Understanding how extrinsic defects influence the domain wall depinning has been an important subject in the area, and various forms of pinning centers have been investigated. Here, for instance, is an experiment by Hayashi and co-workers in Stuart Parkin's group, where they investigated the critical depinning current from a notch for 4 different types of domain walls, meaning transverse and vortex walls. They observed that whereas the depinning using an external field is markedly different for the different configurations, it is surprisingly similar when the depinning comes from spin torque. And this could be due to the fact that domain wall transformation can be induced below the critical depinning current. Another interesting work by Luc Thomas, also in Parkin's group, is shown here, where the depinning is achieved using a current pulse. By changing the amount of current injected in the wire and the pulse duration, they obtain this beautiful picture. The plots show the depinning probability. The blue color means that the domain wall remains pinned by the notch, and the red color means that it has moved out of the notch. What the figure says is that the depinning probability oscillates with the current pulse duration. A one-dimensional model is proposed to explain how this works. The notch constitutes a pinning potential in which the domain wall can oscillate at an intrinsic resonance frequency when excited by the spin torque. When the spin torque is turned off after the current pulse, the domain wall can reach another orbit and get kicked out of the notch. This is what is illustrated on the right figures, which show 3 typical trajectories in phase space for different pulse durations. I know I'm going very fast here, so it can be pretty confusing, so I encourage you to have a look at these very nice papers more carefully. The take-home message is that the interplay between the domain wall pinning potential and the spin torque can lead to a rich depinning behavior. Let's move on to magnetic domain walls with perpendicular magnetic anisotropy. These walls are typically made out of nickel-cobalt multilayers, such as the experiments by Burroughs and co-workers, or using interfaces such as cobalt and platinum. In the case of nickel-cobalt multilayers, clear signatures of thermally activated depinning has been recorded, suggesting that the motion is driven by the non-adiabatic torque. On the other hand, Teruo Ono's group has demonstrated the existence of intrinsic pinning using the same system. The idea is the following. They took a magnetic wire made of nickel-cobalt multilayers and studied the current threshold as a function of the width of the wire. As we know from Lecture 5, the perpendicular domain wall configuration switches from block wall to nail wall when increasing the wire width. So for a narrow wire, the nail wall is favored, and for a wide wire, the block wall is favored. In addition, upon increasing the width of the wire, the magnetic field that you need to deepen the domain wall decreases continuously. So one expects that the current threshold should also decrease when increasing the width of the wire. Indeed, if you need less field to deepen the wall, you should also need less spin torque, at least in the scenario where extrinsic pinning is dominant. But what you can see is that the current threshold reaches a minimum at the very point where nail and block configurations have the same energy. This means that the mechanism for domain wall motion is not the non-adiabatic torque, but rather the adiabatic torque. In other words, the domain wall is in the regime of precessional motion, and its configuration changes continuously between nail and block wall. Now, I want to introduce two intrinsic puzzles that were reported about 10 years ago and whose solutions opened interesting perspectives recently. The first puzzle has to do with the non-adiabaticity parameter beta. As I told you a few slides ago, there's a debate about the physics that is behind this non-adiabaticity. So a number of experimental studies have attempted to estimate quantitatively the magnitude of the beta parameter. And quite surprisingly, it has been realized that this parameter does not really depend on the material itself, but rather on the magnetic texture. For instance, in this work by Matthias Klaue's group, it was reported that in transverse walls, the non-adiabaticity is as large as the magnetic damping. But in magnetic vortices of the very same material, the experiment shows that the non-adiabaticity is about 10 times larger. So that's the first puzzle. The second puzzle was almost unnoticed at the time of its discovery. It concerns the motion of perpendicular domain walls in systems with inversion symmetry breaking, such as platinum, cobalt, and alumina. In these systems, the authors reported gigantic mobility, and because at that time everything was interpreted in terms of adiabatic and non-adiabatic torques, it was attributed to a giant non-adiabatic parameter. But what is even more intriguing is that the wall is not going in the right direction. In these systems, the wall is going against the electron flow, whereas in any other system such as permalloy, the domain wall goes with the electron flow. So that's our second puzzle. Let's consider the second puzzle first, the giant mobility in perpendicular magnetized wires. What the earlier experiments established is that the domain walls move with the electron flow, not against it. The domain wall velocity is much larger than usual in these experiments, and most importantly, inversion symmetry breaking plays a central role. To make progress on this matter, the group of Bert Koopmans studied a trilayer composed of platinum, cobalt, platinum. Here, the authors considered a trilayer in which the top platinum is 2 nanometer thick, while the bottom platinum is 4 nanometer thick, so it is not symmetric. In these experiments, the authors measured the domain wall mobility as a function of the in-plane magnetic field. Normally, this in-plane magnetic field is unable to move the domain wall by itself. In addition, the authors also apply a current that induces some sort of spin torque. So you see that changing the direction of the magnetic field switches the direction of the domain wall motion. In addition, the mobility increases with the field and saturates at some critical value. So that's when the top and bottom platinum have different thicknesses. Now let's see what happens when they have the same thickness. Then what you see that the domain wall doesn't move at all, no matter how large the current or the in-plane field. And to complete the picture, if you reverse the structure, thick platinum on top, thin platinum below, you get the reverse scenario. The domain wall mobility increases with the field and it changes sign with the field direction. At this stage, you might be a bit lost. But you need to convince yourself that this experiment has been instrumental to the development of a robust understanding of the physics at stake. The scenario that explains this behavior has been proposed by several teams, but it has been most clearly exposed by André Thiavel in his 2012 groundbreaking paper. Consider this bilayer composed of a ferromagnet deposited on top of a heavy metal. Due to interfacial anisotropy, the magnetization lies perpendicularly to the plane. The domain wall naturally adopts the block configuration to minimize the dipolar energy. Now, I inject a current density in the bilayer, and because of the heavy metal, because this heavy metal has strong spin-orbit coupling, a spin Hall effect arises that injects a spin current into the ferromagnet. Notice that in the block configuration, the magnetic moment at the center of the walls is collinear to the incoming spins, and therefore the current does not exert any torque on the wall. However, when Jaroszewski-Moria interaction is present, the domain wall prefers the homochiral Néel configuration. In this case, the spins injected via spin Hall effect are aligned on the central magnetic moment, and therefore will induce domain wall motion. You see that the central moments of two consecutive domain walls are opposite, because all the walls have the same chirality imposed by the Jaroszewski-Moria interaction. As a result, the torque on two consecutive walls is the same, so that all the walls move along the same direction. When you apply an external in-plane field, exactly like in the experiment described in the previous slide, you can tune the chirality of the walls. As soon as this applied field exceeds a critical value, that is called the Jaroszewski-Moria field, then all the moments align with each other. This way, the torque will be opposite on two consecutive walls, such that the red domain shrinks, whereas the blue domain expands. Now let's try to be a bit more quantitative. The torque from the spin Hall effect has this expression, where Jc is the current density flowing in the heavy metal, and theta h is the spin polarization of the spin Hall current. It's called the spin Hall angle or the spin Hall efficiency. It's rather easy to do the math, so let's leave it to the fans. Anyway, once you inject this torque in the one-dimensional LLG equation in the presence of the Jaroszewski-Moria interaction, you obtain the velocity of the wall that looks like that. Interestingly, this velocity has a nonlinear dependence on the current density, which is confirmed by the numerical simulations performed by André Thiavel. This scenario has been qualitatively confirmed by many experiments. The current-driven motion has been interpreted in terms of the interplay between spin Hall effect and interfacial Jaroszewski-Moria field, like in the two studies by the groups of Stuart Parking and Geoff Beach. Let me emphasize that this is not the whole story, though. Many inconsistencies have been reported, and this scenario does not explain everything. So keep your eyes open, because the field is far from being closed. Before I move on, I'd like to mention where this research topic is going now. The main motivation for these studies is the development of the racetrack memory device proposed by Stuart Parking in 2008. The centerpiece of this device is a magnetic track on which the domain walls sit and can be manipulated by a current. Important efforts have been paid to optimize the current-driven domain wall motion in perpendicular magnetized wires, such as the one we have seen in the previous slides. To the best of my knowledge, the best performances are obtained using a synthetic antiferromagnet, meaning two perpendicularly magnetized layers coupled antiferrometrically with each other through the RKKY interaction. Parking's team has reported superior performance when this coupling is optimal. Another direction along a similar line considers ferrimagnets, which are magnetic compounds composed of two inequivalent sublattices, typically gadolinium cobalt or terbium cobalt, and that show a non-vanishing magnetization. It has been experimentally observed that the velocity of ferrimagnetic domain walls reaches a maximum at the compensation point, when the magnetic moments of the two sublattices compensate. This could be a powerful alternative to the synthetic antiferromagnets for racetrack memories, among other things. Now I want to address the other puzzle I mentioned earlier. I was saying that the non-adiabaticity might be different in transverse walls and vortices. More generally, I'd like to take a closer look at the spin transport in complex magnetic textures, such as this one. To understand how spins propagate in a system where the magnetization varies both in time and space, I need to perform a rotation of the coordinates in order to look at the spin in the frame of the local quantization axis. Concretely, in the Hamiltonian given above, the global quantization axis is along z, whereas the magnetization varies in space and time. So what I want to do is to change the quantization axis and set it along the magnetization direction. I can do that by using this rotation matrix, defined in spin space, and where n is the direction around which I perform the rotation. I can write the wave function psi in the global frame as a function of the wave function phi in the local frame. After some algebra, I obtain the Schrödinger equation in the local frame. I really encourage you to do this calculation. It's not very difficult and you really see where the different terms are coming from. What is fascinating is that you can demonstrate that the new Hamiltonian has acquired new terms that behave like an effective electromagnetic field with a scalar potential and a vector potential that depend on the spatial and time derivatives of the rotation operator. These new operators can be written explicitly as a function of the spatial and time derivatives of the rotation axis m, which itself depends on the direction of the magnetization m. So clearly, a spatial and time varying magnetization act like an effective electromagnetic field on the conduction spins. And that's super exciting. Let's push the theory a bit further and make a strong assumption. We'll assume that the magnetic texture is smooth and slow. Or in other words, it varies over distances and times that are both very long compared to the intrinsic conduction spin dynamics. If this is so, I can consider that the spin is always aligned on the local magnetization. I can then project the scalar and vector potential operators on the spin state and obtain the effective spin-dependent electric and magnetic fields, which look like that. Again, these calculations are only valid for a magnetic texture that changes smoothly in space and slowly in time. This method is really powerful because we get an explicit form. You see that a magnetic texture that varies both in time and space produces a spin-dependent electromotive force, whereas a static magnetic texture that varies along two spatial directions can create an emergent spin-dependent magnetic field. Let's see how the conduction spins react to these fields. Imagine I have a magnetic texture that changes over time, and I apply an external electric field that generates a spin-polarized current. I can write the current for spin S in the local frame in the following way. The first term is the drift due to the electric field, and the second term is a drift due to the emergent spin-dependent electric field that it comes from the moving magnetic textures. This emergent electric field is usually called the spin motive force. In addition, due to the emergent spin-dependent magnetic field, I should have an emergent Lorentz force that is driven by the external electric field. Finally, the cooperation between the emergent electric field and the emergent magnetic field produces what I call a spin motive Lorentz force. In this phenomenological model, I simply need the spin conductivity and the electron charge density, since the dynamics of the magnetic textures is encoded into the emergent electromagnetic field. Okay, so let's compute the total charge current that flows in the system. For transparency, I have written the explicit dependence of these different terms on the spatial and temporal gradient of the magnetization. So I have four terms. The first one is the usual Drude conductivity, so I won't talk about it. The second term is the charge current that is driven by the spin motive force. It is proportional to both the time and space derivative of the magnetization. Concretely, if you have a moving magnetic domain wall, it will generate a charge current along the direction of the domain wall motion. This idea was proposed originally by Berger in 1986 and revived by Barnes and Maekawa 20 years later. What is interesting is that for a transverse domain wall, the current is proportional to the time-average time derivative of the azimuthal angle. So it means that in the flow regime below Walker breakdown, the current vanishes. It is non-zero only in the precessional regime, a fact that has been confirmed experimentally by the group of James Erskine. In this figure, the open symbols represent the field-driven domain wall velocity, and the black symbols represent the voltage measured along the magnetic wire. It's clear that you only get a voltage above the Walker breakdown. The spin motive force has also been measured by Teruo Ono's group using an oscillating magnetic vortex. You can see the beautiful oscillation of the current that corresponds to the vortex core passing through the detector periodically. Let's look at the third contribution to the current, the emergent Lorentz force. As we have seen above, when the magnetic texture is 2- or 3-dimensional, an effective spin-dependent magnetic field can emerge that is related to the curvature of the magnetic texture. This emergent magnetic field induces a spin-dependent Lorentz force on the conduction electrons, and because the current is itself spin-polarized, we end up with a so-called topological Hall effect that is driven by the curvature of the magnetic texture. You can notice that to obtain the topological Hall effect, you need a certain chirality, otherwise there is no effective Hall current. This effect has been observed in chiral magnets such as manganese silicon and is usually considered as a signature for skyrmions. We'll come back to that in a moment. The last term I want to talk about is this one, that comes from the combination of spin motive force and the emergent magnetic field. In other words, when a skyrmion is moving, or any magnetic object with a non-trivial topology such as a magnetic vortex for instance, then it pumps a charge current. Because of the topology, you don't need to be in the precessional motion regime to generate this current. It actually works even in the steady state regime. This is what we computed a few years ago by solving the time-dependent Schrödinger equation on a moving skyrmion. You see that a current is pumped along the wire, which should be experimentally detectable. We have considered the charge current. Now we can look at the spin current induced by the emergent electromagnetic field. Since we are in a magnetic texture, we can take its divergence and obtain the spin torque. We end up with this rather long expression. Now let me walk you through it. The first term here is the adiabatic torque due to the external electric field. The second term is a torque that comes from the non-trivial topology of the structure, and it turns out that it acts like a non-adiabatic torque. This is why we call it the non-adiabatic topological torque. We proposed this torque a few years ago, and at that time, we were collaborating with the group of Matthias Klawi to understand the reason why the non-adiabaticity was severely enhanced in magnetic vortices. As we understand it, this torque comes from the presence of a spin Hall current induced by the non-trivial topology, which induces a local non-adiabatic torque on the vortex. In addition, this torque is proportional to the gradient square, so it increases when we reduce the size of the magnetic object. Beside this torque, the magnetic damping is also affected. It possesses a term that is directly related to the spin motive force and that is quadratic in gradient. Again, the shorter the domain wall, the larger the magnetic damping. This idea was proposed by Shufang Zhang in 2009. Finally, the damping also possesses a contribution that is related to the topology of the system. Since a skyrmion or vortex pumps a spin current while moving, its magnetic damping is also enhanced. For the last few slides, I want to talk about a very hot topic in Spintronics, which is the current-driven dynamics of magnetic skyrmions. It turns out that their properties share a lot of similarities with that of magnetic vortices, so I will treat them on equal footing. To describe the Skyrmion of vortex dynamics, I will adopt the formalism proposed by Thiele in 1973. The idea is to consider that the Skyrmion or the vortex remains rigid during the motion. So I'm looking for a way to represent its dynamical properties using an equation of motion in the same spirit as Newton's equation. Look at the LHG equation. You remember from a previous lecture that this term is a thermodynamical force, which is the functional derivative of the magnetic energy with respect to the magnetization vector. From the magnetic energy, I can also define a mechanical force that is associated with the derivative of the magnetic energy with respect to space. When the magnetization varies in space, I can express the mechanical force in terms of the thermodynamical force. Now I want to see how this mechanical force is related to the motion of my rigid magnetic texture. To do so, I need to express the thermodynamical force using the LLG equation. I now assume rigid motion, which means that the time derivative of the magnetization is proportional to the velocity. I will also express everything in the spherical coordinates, and finally get this expression for the thermodynamical force. After integration over the magnetic volume, I finally get Thiele's equation of motion that describes the rigid dynamics of a magnetic object. This equation is composed of three terms. First, we have the driving force, which can be the gradient of an external magnetic field or spin transfer torque. The second term is a cross product between the velocity and a vector g that is called the gyrotropic vector, and that is a quantity that is solely governed by the topology of the magnetic texture. No topology, no gyrotropic vector. The last term is also proportional to the velocity, and its magnitude is controlled by the dissipative tensor proportional to the magnetic damping. So in summary, this equation is a balance between an external force, an internal gyrotropic force, and a viscous force. The cross product that is at the center of Thiele's equation is responsible for the Skyrmion or vortex Hall effect. We will first look at how a charge current can drive a magnetic vortex into motion using our newly derived Thiele equation. In this scenario, the vortex is driven by spin transfer torque, and to obtain analytical formulas, we will assume a rigid, isolated vortex. This vortex is characterized by an outer radius, uppercase R, and an inner radius, lowercase a. You can find details in this publication. This definition enables us to get explicit expressions for the gyrotropic vector and the dissipative tensor. Here, P is the polarity of the vortex, up or down. Now, in a real material, a magnetic vortex usually separates two in-plane magnetic domains, like here. You see that our magnetic vortex separates a domain with magnetization pointing right from a domain with magnetization pointing left. Fine. So when I inject a charge current in this magnetic wire, the current exerts a torque on the vortex and it pushes it along the direction of the current, but also transverse to it. This transverse motion is directly related to the gyrotropic vector and is sometimes referred to as vortex Hall effect. The explicit expression of the velocity is given here and shows that the longitudinal velocity is simply proportional to the adiabatic torque, whereas the transverse motion is a balance between the non-adiabaticity, beta, and the magnetic damping, alpha. So naturally, the vortex should move towards the edge of the magnetic wire. And when it reaches the edge, then something else happens. Of course, we still have the longitudinal and transverse forces applied to the spin torque, but they are balanced by the reaction of the edge. This reaction cancels the vortex Hall effect so that only the longitudinal velocity survives. A small calculation indicates that in this case, the longitudinal velocity should be proportional to the ratio between the non-adiabaticity and the magnetic damping, which is pretty much similar to what we obtain in the case of the one-dimensional magnetic domain wall. A nice illustration of the central role played by the gyrotropic force on vortex dynamics has been demonstrated experimentally by several teams, including Vincent Crowe's team at CNRS Thales Joint Lab, Teruo Ono at Kyoto University, and Dan Ralph at Cornell. The competition between spin transfer torque and the gyrotropic force induces vortex oscillations, which produce radio frequency signal at resonance. As we have seen in the previous lecture, you can put several of these oscillating vortices together and synchronize them to get very fine and powerful signal. The precise mapping of the vortex trajectory can provide very interesting information about the torque itself. Using scanning transmission X-ray microscopy, the group of Matthias Klaue at the Johannes Gutenberg University in Mainz has allowed us to better understand the physical origin of the gigantic non-adiabaticity that has been reported in magnetic vortices. Indeed, because of the non-trivial topology of the magnetic vortex, a topological torque emerges that enhances the non-adiabaticity. The same thing happens in skyrmions, by the way. Pretty neat, isn't it? Finally, I'd like to show a last beautiful experimental result obtained in the group of Teruo Ono. They showed that the resonant excitation of the vortex using a spin polarized current can lead to the controlled reversal of the core magnetization, which happens within a few nanoseconds. This lecture would not be complete if I didn't talk about skyrmions. As you may already know, magnetic skyrmions are topological magnetic defects whose chirality is governed by the Jaworzynski-Moriah interaction. So they only appear in systems lacking inversion symmetry. The first experimental observation of magnetic skyrmions was reported in the groups of Yoshinori Tokuro at Riken and Christian Fladerer in TU Munich. They worked with non-centrosymmetric weak ferromagnets such as manganese silicon or iron cobalt silicon compounds. In these materials, the weak exchange competes with the Jaworzynski-Moriah interaction. And the Jaworzynski-Moriah interaction is so strong that it stabilizes a crystal of magnetic skyrmions. In other words, the skyrmion crystal is the ground state, so it is very robust. Here I give an example of the image obtained by Lorentz force microscopy on iron cobalt silicon at low temperature. This image was taken by the group of Tokura. The problem you see is that this specific ground state only appears when applying an external field and at low temperature. So it's very beautiful but not very practical for experiments. Because the skyrmions form a periodic array, they can be studied using diffraction methods. In this figure, the diffraction pattern is recorded while injecting a current in manganese silicon. You see that the pattern changes upon switching the current polarity, which means that the skyrmion crystal has rotated. This is an evidence of spin transfer torque. What was particularly exciting with this experiment from the group of Christian Fladerer is that the critical current needed to modify the pattern was about 2 orders of magnitude smaller than the critical current used to move domain walls. A few years after these discoveries, Spintronics experimentalists discovered magnetic skyrmions at room temperature using metallic multilayers, harvesting the rather strong Jaworzynski-Moriah interaction at transition metal interfaces. These skyrmions present a very important difference compared to those reported in bulk non-centrosymmetric magnets. Indeed, since the magnetic exchange remains very large, the Curie temperature is like 1000 Kelvin or so, these skyrmions are not the ground state. They are metastable and do not form a crystal, which is great, because it means that one should be able to manipulate them individually. The electrical control of magnetic skyrmions is currently a very hot research topic, as skyrmions could be used for racetrack memory applications, as well as in artificial synapses for neuromorphic computing, for instance. From the theory standpoint, though, the physics shares a lot of similarities with magnetic vortices, and in particular, magnetic skyrmions experience the so-called Skyrmion Hall effect.
In this part, we have seen how adiabatic and non-adiabatic torque can lead to domain wall motion, and how the cooperation between Jaworzynski-Moriah interaction and spin Hall torque can lead to gigantic velocities. We have also learned that when a magnetic texture extends over 2 or 3 dimensions, the conduction electrons experience an emergent electromagnetic field. In a sense, the magnetic texture tricks the electrons and forces them to behave as if they were such an external electromagnetic field, leading to emergent Hall effects and topological torque, for example. Finally, we talked about how spin currents can move vortices and skyrmions. and will outline some of the important features of the dynamics. This concludes this series of lectures on spin electronics and magnetism. If you have been following us since the beginning, you're a hero. So, thank you very much for sticking with us, and we hope you enjoyed it. If you did, please don't hesitate to give us a thumbs up. And I would like finally to warmly thank Joanna Ugieglo, who has been putting an extraordinary dedication and energy into this project. We're looking forward to hosting new projects on other exciting aspects of quantum matter physics, and we'll see you around.